All right. All right, so the bonus here. So you had to set up a law of cosines on this one because you have a triangle and you know x is changing and you know the angle's changing. So you set up law of cosines. You're given the d theta dt. You're told what the RPMs are of the crank. So you have to convert that in from revolutions per minute. You have to convert it all the way over to radians per second. That's the first thing. That's your d theta dt. And you want to know dx dt, how fast the piston's moving. So here's your equation relating x and theta. You differentiate and plug in. I mean, it's not, I'm trying to think if there was anything special. You wanted to know when the crank was, I forgot the problem. Yeah, so, when the crank arm is horizontal. So when this arm is down here or over here, in either case, you get a right triangle. So when you have a right triangle, your theta over here is going to be pi/2. So that's the basic overview of it. I won't go into any more on that.
Okay. Oh, it actually had it a little better than I thought I did, apparently.
I think you had law of cosines going.
Yeah, I did something wrong in all my conform calculations, and I couldn't get anything that made any sense, you know?
No.
So I don't know.
Okay. All right, so today we're doing 4.1. We're starting chapter 4, okay, which is applications of derivatives. And then Thursday, I've already told you that I'll be out of town, and so we're not going to have class. I've already made a video. I have not put it in YouTube. Wait, did I uploaded it? I think it's there. Hold on, let me see. Refresh it. Yeah, it's there. It may not be high quality yet, but it's there. It's short. It's not a long video, 36 minutes. So it's a short video on section 4.2. And then after that video, you should be able to do the homework for that. All right. So that's what we will say is our class on Thursday. So don't show up to Zoom. I won't be here. And then a reminder that this Friday is the last day to drop. That's why we took the exam on Friday. I mean, I'm sorry, on Thursday last week. That's why we did it. So you would have time to determine, your stance in the class. Even though I'm going to be out of town, I will be available if you need to get in touch with me. Text me, call me, email me. If you're concerned about your grade or something like that, let's get that fixed, or at least get it understood before Friday, because after Friday, you got to finish the course out. Whatever your grade is, your grade is. So yeah, I'll leave that up to you. If you do want to drop this class or any class, okay, the procedure on that is to go through the registration system and initiate the drop on your own. If for some reason you can't figure that out, make sure you at least email your professor, let them know you want to drop, and do that before the end of business on Friday. So 5 p.m. on Friday. All right. Any questions before we begin?
I guess. Are we done with L'Hopital's rule?
Oh wait, yeah, we got a little L'Hopital. I'm sorry, I have it ready to go. I don't know why I didn't mention it here. Yeah, we got to start with L'Hopital. Thank you. Don't worry, it was going to be my first page. I would have brought it up. So we had started doing these special forms right here, right? We had done an example of 1 to the infinity. We talked about why it is an indeterminate form. We still have to look at 2 other forms, and I'm going to hit one more example of the infinity minus infinity. So I have an example of 0 to the 0. I have an example of infinity to the 0, and then I have an example of infinity minus infinity. We're going to do these 3 limits. We're going to wrap it up. We're going to move into chapter 4. So let's take a look at this first limit we're trying to establish. And remember L'Hopital's rule, right? L'Hopital's rule says if you have 0 over 0 or infinity over infinity, you can just take derivative of the top and bottom separately and then just find the limit. So here we have 0 raised to the 0. Let's verify that. So if I let x approach 0, sine of 0, we know that heads to 0, right? And in fact, when we head to 0, if you think about the sine function, right? Sine looks like this. If we're approaching 0 from the right side, we are coming into 0 like this through positive numbers, aren't we? It's headed to 0, but those numbers are above the x-axis. So those are little tiny little positive numbers right here. And then we're raising this to the 0. So this is where you have a conflict, right? Because 0 raised to any power should be 0, but any number raised to 0 should be 1. So there's that conflict. And I talked in depth about this last class, that I'm not telling you that 0, take the number 0 and raise it to the 0 has any meaning. I'm saying in the limit, if we get something that looks like that, then we can start doing something. So let's do it. What do we do? Well, we do exactly the same thing we did when we had 1 to the infinity. We're going to call this limit, we're going to call it y. And then we're going to bring in the natural log on both sides. We're going to pass the natural log through the limit. And by bringing the natural log in front of this sine of x to the x, that then allows us to take that x and pop it out in front of the natural log. So my next line, natural log y equals limit x goes to 0 from the right. I have x now in front of natural log of sine x. Now, if you look at the limit, what we have here, what's happening now is that this is going to 0, and this is going to natural log of 0. What does natural log of 0 go to? Because natural log of 0 is undefined. But as we get closer to 0, what does natural log do?
It goes towards negative infinity.
Okay, so if it goes to negative infinity, right? Dives down. We have to go back and look at the graph of natural log. Or actually, we need to have a mental picture of what that looks like, right? So that heads to negative infinity. So now we're in a different form, right? 0 times infinity. So how do we handle that? Take one of them and drop it, right? Drop it down. So I'm going to pick the easier looking one, the x, and I'm going to drop the x down. And when I drop it down, I'm not like literally just putting x down there. I'm just rewriting it in a different way so it looks different, right? It's the same exact expression, except I'm writing 1 over x on the bottom, because I know if I flip that x back up, I get back the original part here. So it's just a different way of writing it. And then I can kind of go through it again. What happens as x goes to 0? Well, we know this natural log thing goes to negative infinity.
That would go to positive infinity on the bottom.
1 over 0, yeah, that right there is going to go to infinity, because now you have a fixed number over 0 that gets big, right? Becomes infinitely large. So we have finally converted something that started off looking like 0 to the 0. We've converted it into something that looks like infinity over infinity. And so we can use L'Hopital's rule. That's the standard procedure, okay, for anything that looks like 0 to the 0. Log on both sides, drop the power out, drop one down. You should get infinity over infinity or 0 over 0, L'Hopital, and then get an answer. So I think I might run out of room here. Let me do this. Move this up, make it smaller. Let me just move all of this up. And then, okay, so now natural log y equals limit x goes to 0 from the right. I'm using L'Hopital, so I'm put a little L here, circle it, you put an H, doesn't matter. Now I need to take derivative of the top. So derivative of the top is derivative of a natural log, which should be 1 over whatever's in there times the derivative of what's in there, which is really just the derivative of what's in there over what's in there. So you can put the cosine on top of the sine, doesn't matter. Is that okay? And then on the bottom, we take the derivative of 1 over x. Be careful. You don't just take derivative of x, right? It's 1 over x. So remember, 1 over x is the same as x to the negative 1. When we take that derivative, you get negative 1 over x squared. I think we did that several times last class. So I'm hoping that everyone's comfortable with the idea that the derivative of 1 over x is negative 1 over x squared. Right? Now, what the heck do we do? Let's flip that. Let's flip things up. I'm going to just bring this over here. This is natural log y equals limit x goes to 0 from the right. I have cosine x over sine x times, I'm going to bring this up, flip it, so it becomes x squared on top, and on the bottom I have -1. Let's just do that. So now at this point, we're going to do something. Notice that if you let x go to 0 right now, this goes to 1, right? This goes to 0, and this goes to 0, and then of course this is just -1. So the only things that are causing problems here are the x squared and the sine x. That's what's causing the issue, right? That's the 0 over 0. So this is something you can do with limits, is if you have pieces that are not affected by the limit, you can break this into two limits like this. I'm going to put the cosine x over -1, then times the limit x goes to 0 from the right of x squared over sine x, like that. You are allowed to split limits up like this. Okay, if there's multiplication between things, you can split it into multiple limits with multiplication between them. That's something you can't do with derivatives, right? If you take the derivative of something, a product, you have to use a product rule. But when you do a limit of a product, you can do the product of the limits. You can split it up. Now, the reason I did that is because this one right here, this is straightforward. If x goes to 0, cosine of 0 is 1, 1 over -1 is -1. Then times this one, what do we have?
0, 0.
0, 0. But I can use L'Hopital now, right? I can use L'Hopital because I have 0, 0. So I'm going to say equal. Don't forget, we have on the left side, we still have the natural log of y, right? Was equal to, by L'Hopital's rule, I'm going to do the limit as x goes to 0. Take derivative of the top, which is 2x, derivative of the bottom, which is cosine x. And now let x go to 0. And you get 0 on top, and you get 1 on the bottom, right? 0 over 1, that's okay. 0 over 1 is 0. So we get here natural log y equals -1 times 0, which means that natural log of y equals 0. And now we want to know what y is, right? Isn't that what we wanted? What's y? Y is this limit, right? What we know right now is what natural log of y is. So to get y, we have to kill off the natural log. So we come in here and we compose both sides with e. So e to the natural log of y is y, and e to the 0 is 1. So I'm basically taking e and raising it to both sides. So our answer is 1. Questions?
So instead of breaking it up, could we just change that cosine x or sine x into like cotangent x? Did that do anything?
I don't think cotangent would have gotten you anywhere. Because you still wouldn't have had the ability to do L'Hopital's rule. Well, yeah, because cotangent of 0 is going to be infinity. I guess you could, but the derivative, see, by splitting it, I don't have to take the derivative of the cosine ever. Like all I'm doing is derivative of these. So I think it helps with the algebra.
What about,
I'm not going to say you couldn't do it with cotangent. I'm just saying I think it would be much harder.
why couldn't we say that that's a constant over in, it's because it's not. Never mind.
Okay, so that's an interesting problem. I think I'm going to need a new page for this one. So let's do this one. So x is going to infinity. Oh, do y'all want to see that last one? I can graph it real quick for you. It was sine x raised to the x, right? And ooh, it's cool looking. We wanted to know what this graph was doing as we approached 0 from the right. And if you look at it, here's the graph. As we come in, here's 0. If we come in from the right, it is approaching 1. Now at 0, it's undefined. Okay, at 0, it's undefined. But as we come in from the right, it is approaching 1.
Yeah. What was it doing on the other side of the 0? Was that it bugging out?
Well, the problem is when you get over here, right, you get some negative numbers in here, and it's starting to it's freaking out whenever you try and put negatives down here. If your base is ever negative, because negative numbers raised to numbers that aren't integers, like if I tell you to take -2 and raise it to the like -2 raised to the -0.56, like what is that? You know, you start to get imaginary numbers, and so things start to really fall apart, which is why
it was doing all those weird dots everywhere.
That's why it was doing all those weird things. Anytime the base was negative, we start having problems. So you can see here that we have problems in a little region right here, because that's where that sine graph goes below the x-axis, and so it's having issues. If I were to label this stuff with pi's instead, you can see that between pi and 2 pi, that's where the sine function goes below the x-axis. And so this thing is having major trouble taking negative numbers and raising them to positive powers. It's just having issues. So
interesting.
Yeah, that's why when we define exponential functions, when we define an exponential function in college algebra, we make sure we have a restriction on that a. We say it has to be positive and not 1. The reason we say it's positive because once it becomes negative, things get weird. All right, here we go. Taking a look at this one. Now, I already told you what form it is, but let's just verify. If I let x go to infinity, of course, 1 plus infinity squared, that's infinite. That's getting huge, right? But 1 over x, that is approaching 0. That's fixed over infinity, right? That gets squashed down to nothing. So you have something that wants to get bigger and bigger and bigger, but the exponent is sitting there saying, hey, wait a minute, I want to raise you to the 0 power. Anything to the 0 should be 1. So you've got that tug of war happening, right? Don't understand that? There's this battle. So let's see who wins, or if they compromise, or what happens. So same procedure as before. We're going to call this thing y. We're trying to figure out what this is. And then we're going to take the natural log on both sides. We will pass the natural log through the limit. And I'm going to go one step ahead. I'm going to pull the 1 over x out now. And then I have to drop 1. You can confirm for yourself right now if you like. This goes to 0, and this goes to infinity. So we have 0 times infinity now. And so when I do my dropping, I'm going to drop 1 over x to the bottom, which really means it's what down there?
Just be x, right?
Just x, right? Because it's really just like 1 over x. That's just x itself. And now I should have infinity over infinity. Verify that for yourself. Just look at it. Top goes to infinity. Bottom goes to infinity. L'Hopital is in play. Here it comes. Derivative of the top. I'm going to write it like this. It's the derivative of the inside over the inside. See, when I do derivatives of natural logs, I either just do it like this, or I do it like piece by piece. I do 1 over whatever's inside times the derivative of what's inside. It turns out to be the same thing, right? Either way. And then the derivative of the bottom is 1. So I don't even need to worry about the bottom anymore. If I let x go to infinity, I still get infinity over infinity, don't I? So I can do L'Hopital one more time. If I do that on the top, I get what? 2,
Two.
right? And then the bottom, I
Yeah.
get
2 over 2x,
2 over 2x. And then now let x go to infinity.
you get 0.
You get 0. So natural log of y equals 0. And then I do e on both sides again to get that y out of the natural log. And we got the same answer as the last one, right? 1 again. That's it.
That was a good bit simpler than the last one.
Yeah, that the algebra there wasn't as bad. Let me graph it. If we take 1 plus x squared and we raise it to the 1 over x, and it's this blue graph, we are headed to infinity, right? We need to go out to infinity. So let me graph y equals 1. There's the line y equals 1. That blue graph should be getting closer and closer and closer and closer. It takes a while, but it gets there. It gets closer and closer and closer to 1. All right. And we showed that with the limit.
Can you kind of explain like what's the giveaway of why you want to like, drop it in order to use L'Hopital's rule?
Anytime you see 0 times infinity, you want to drop 1. That's the giveaway. So right at this step right here, that goes to 0 and that goes to infinity. Right? Because as x gets big, 1 over x gets small. This gets infinitely large, and then the natural log function, as you go to infinity, grows. It slowly grows, but it grows, right? So that's the giveaway right there.
Now, does this prove that infinity to the power of 0 will always be 1, or
No.
does it really depend on the equation?
It depends on the actual function itself.
Okay.
Yeah, it's not, yeah, when you look at these forms that we have, it's not like what we're not doing is this. We're not saying anytime you see infinity to the 0, you get 1. We're saying anytime you see infinity to the 0, you have to do all of this and then see what the answer is. It could be 1, it could be 0, it could be infinity, it could be e, it could be any really, it could be the number 2. You have to crank it out, right, to see what happens. Now, in a lot of the problems in the book, it turns out to be 1 or 0 or something nice, but generally speaking, you have to actually evaluate it to figure out what the limit is. Okay, so the last one here, I'll just do it here. We have an example of infinity minus infinity. Now, we did do these problems months ago, when we were doing first learning limits, and I told you whenever you see infinity minus infinity, that you need to think about factoring. So look at this example. Let's first verify that we are getting infinity minus infinity. If x goes to infinity, that becomes infinite. And then minus, well, natural log of infinity is also infinite. So we're subtracting 2 infinities. That is indeterminate. That is not 0, right? That is not 0. If it were a plus in between, you could say the answer is infinity, if it was a plus. But it's a minus. So you don't know. Big number minus big number, you can't tell who wins. So we need to do something. Well, we need to factor. There's nothing obvious to factor here. There's nothing obvious to factor. So what I'm going to do is I'm going to force a factoring. I'm going to factor out the square root of x. And when I do that, I'll get a 1 for the first one because I pulled that square root of x out. But on the other one, because there wasn't a square root of x there, I have to rewrite this as natural log of x over the square root of x. Now, if that seems awkward to you, then just multiply the square root of x back through, and you'll see that if I do that, this times this is this, and then this times this, the roots cancel, and you just get back the natural log of x. So that's something you can always do when it comes to algebraic expressions. You can always factor whatever you want out. And then what happens is each of the terms gets divided by that factor. So that does work. And now if I look at these limits, this goes to infinity, right? Times, now I have 1 minus, now what does this one go to? If I let x go to infinity, what do I get on top?
That's infinity over infinity.
Over infinity, right? Infinity over infinity. And that, we don't know what that is, right?
Yeah.
We don't know what that is. So what I'm going to do is this. I'm going to do a little sub problem within the problem. I'm going to do a separate limit over here, and I'm going to try and figure out what this is. What is that limit? Okay, so I'm trying to figure out what this goes to. So if I take this limit, I get infinity over infinity. So I can apply L'Hopital's rule. And I can take the derivative of the top, which is 1 over x. And then the derivative of the bottom is 1 over 2 root x. You know that because we've done that about, I don't know, 100 times now, taking derivative of the square root of x. And now I'm going to flip this up. One over x times 2 root x over 1. Clean this up. 2 root x over x. We can simplify this. There's algebra to do here, right? Because the bottom, you can actually look at the bottom as being root x times root x, right? That's one way I could do this. You could also just mess with properties of exponents, but I like doing it this way because then you can just see they cancel. So you get 2 on top and root x on the bottom. And now let x go to infinity.
We approach 0.
You get 0 here, right? Make sense? So let's go back over here where we were. We've said that this part in red, we kind of didn't know what it was. It was infinity over infinity, but we just figured out that that's 0. So I know that this piece is actually not headed to that, it's headed to 0. So that means the inside here is headed to 1, right? And then 1 times infinity. Well, that should be going to infinity, shouldn't it? It's just a huge number times a number that's getting close to 1. Those numbers, that's all good. That's not indeterminate. That should be infinite. So this just shows you how you can factor something out, which is weird. And then within a problem, if you're having trouble with one of the parts of the limit, you can just go do that on its own and then bring that answer back in. Yeah, graph. You want to see the graph? Okay, so this one is square root of x minus natural log x. Let me turn the other ones off. So here's the graph of this, and we want to know what's happening as you go out to infinity. So you can see as you go out to infinity, this thing starts to grow. And it just keeps growing and growing and growing. The further out you go, the more it grows and grows and grows. Which that's what we determined, right? Algebraically. All right, so that's it. I have a little summary here, a recap of limits here with L'Hopital's rule. You know, if we ever see 0 over 0 or infinity over infinity, we just use the rule, right? Derivative top and bottom, do them separately, boom, crank it out, see what happens. Maybe you have to do L'Hopital a few times, whatever. But 0 over 0 or infinity over infinity, that's what we like to see. Now, if we see 0 times infinity, right? That's the key to let us know to drop something down, right? We drop one of the factors down, then we use L'Hopital. Now, if we see 1 to the infinity or 0 to the 0 or infinity to the 0, any of these forms, then it's a little more involved. We have to set the limit equal to y. We do the natural log on both sides. Once we do that, we should be able to drop, then it'll look like 0 times infinity. Then we'll drop one of the factors down and then use the rule. And then infinity minus infinity, we will factor something out, create some fraction, and then use the rule. And that's pretty much it. I'll post that in the notes later and you can go back and reference that. So I'm ready to move on, but let me just throw this out here for you. what if you have this? Limit x goes to infinity of 1 over x to the natural log x. Take a minute to think about that. So what form do we have here? Where's the base headed? Where's the exponent headed?
Is it 0 to infinity?
Zeros.
And how do we handle 0 to the infinity?
Natural log of y.
Yeah, so that you start thinking, oh, well, we've seen this before, right? Like 1 to the infinity and all that. So you start thinking natural log. So I set the trap for you and I got you, okay? This is not an indeterminate form. Think about what's happening here. You have a number, right? You have a number here that's getting really small, right? Imagine it, imagine that number. Maybe it's like 1 over, I don't know, 1,000,000 or something like that, whatever, right? And then what are you doing? You're taking that number and you're raising it to a number that's getting big, right? A big number. So maybe I'm raising that to the 1,000,000th power or 2,000,000 power or 10,000 power. What happens to a small number when you raise it to a big power?
It
What
gets
happens?
increasingly smaller.
It gets smaller. Think about that. Let's take a small number. Now I know 1/2 is not small, right? But take 1/2 and raise it to the 4th power. Did it get bigger or smaller?
It gets smaller.
It got smaller, didn't it? It got smaller. So the way you want to look at this is like the base, right? The base is like, hi, I want to be small, right? And the exponent is trying to get big. The exponent sitting there going, oh, you know what? I'm going to help you get smaller faster, right? So there's no calculus to do here. This is just purely, oh, it's headed to 0. That's it. That's why when I gave you this table, I didn't put 0 to infinity on here because that's not an indeterminate form. What happens is students will they'll think that any combination of 0 and infinity and 1, like all those different combinations are indeterminate forms. They aren't. 0 to the infinity is not indeterminate. What about this? How about if you had infinity? No. How about something that was approaching 1 to the 0? Would that be indeterminate? So the base wants to be 1, but the exponent wants to be 0. Would that be a problem?
No.
No, the base wants to be 1. And then when you raise things to the 0, what does that do?
Should just make it
Turns
1.
it into 1, right? So it's like they're helping each other out, right? That's kind of what's happening here. Base wants to be small. Oh, I will help you. Base wants to be 1. Oh, that's exactly what I like to do to numbers, right? It's like they're teaming up and they're helping each other instead of this where they're in complete conflict with one another. You'll see the difference? So you just have to be careful because some things are indeterminates, some things aren't. Now, I'm not going to throw a problem at you like that on a test where I'm like trying to trip you up and trap you. But don't just automatically think anytime you see any form of this that you automatically go to the natural log, right? It's just, you have to pay a little attention to it. And I don't believe that the book in any of the exercises gives you something like that where it's not indeterminate. So, but in the real like math moving on later, there will be problems that you run into where it's not indeterminate. So don't go spend time trying to do something because you're really just kind of wasting your time. Now, I'm wondering, could if we did do it, would we still determine the answer 0? So like, if we weren't paying attention, and I don't mean this in a bad way, okay, because I was trying to get people, I'm sure a lot of people were ready to go with natural log on this, okay? If we did it, will we get it wrong? Let's see. If we did natural log here, limit
Raised to the infinity.
x goes to infinity. I'm sorry, did
Hello?
someone say something?
Can you hear me?
I heard like a mumble.
Hello?
Yeah, yes, what?
Oh, okay, there we go. So anytime we have the 0 raised to the infinity, is it automatically gonna be 0?
Yes.
Okay.
Yeah.
I just wanted to make
because-
sure that that
Yeah,
was a
because they
rule.
help each other out, exactly. There's only one thing it can go to. Yep. What the heck did I, yeah, so I brought down the natural log, right? So I brought the natural log down, but I had to take natural log of 1/x. And then I would drop one of them down. This is the part that'll be ugly, because I don't know which one really is better to drop down. So I'll drop the first natural log down. And be real careful when you drop down, it has to become 1/natural log of x. And now I can I even do L'Hopital? Let's see. I can't even do L'Hopital. I can't do L'Hopital. It's not allowed. Why? Think about what's happening here. Well, shit, I should have done it here. How about here? Where is this headed?
Infinity.
Infinity, right? Times, okay. This is going to 1/0, right? Okay,
Yeah,
what is natural log of 0 headed to? Where's the natural log?
Undefined, I'm pretty sure.
0. As you head to 0. Remember, as you head to 0.
That was negative infinity.
Negative infinity, right? This is the natural log function as you head to 0, right? Because as x gets big here, that becomes very small. It heads to 0. The natural log of something headed to 0 is going to negative infinity. Look, we don't even have 0 times infinity. We have what? Infinity times negative infinity, right? Which should be what?
Just be infinity, negative infinity.
Negative infinity, right?
Yeah.
Negative infinity. So we have natural log of y is headed to negative infinity. When does the natural log function go to negative infinity? Do e on both sides. This it's not making sense. Okay, this is e to the y. You get, what's e to the negative infinity? What happens to the e function as you go to negative infinity? There's e to the x. What happens as you go this way? Where's it going?
It's like it's approaching 0.
It's approaching 0. And that was the answer, okay? But the thing is, you cannot use L'Hopital here because you don't have what you need. You don't have 0 0. You don't have infinity over infinity. In fact, here, you don't even have indeterminate. This is not indeterminate. This is infinity times negative infinity. That is a huge negative number. Okay, let's move on. We can get lost in this. So chapter 4, applications of differentiation. So this first section is really important, all right? What our plan here is, because we are running low on time in this class, right? We're behind. I'm definitely going to make sure we do this. You're going to do that at home. And I mentioned this in the video. This mean value theorem section is, if I had to trim it out of the class, I could. I mean, I wouldn't want to, but if I had to, I could, because you could still survive the rest of the way without it. Derivatives and shapes of graphs, absolutely, we have to cover that. Curve sketching. This one, we don't absolutely have to do, all right? What this section is about is it's about how we can use all the calculus that we've learned to draw a very accurate graph for a function by hand. That means we can figure out where all the curves are supposed to go, where everything, where the highest and lowest points are. We can get a very accurate picture of a function, which was extremely useful before computers, right? Before computers, when mathematicians, physicists, chemists had to figure out what a function looked like, the only thing they had was the calculus, and they get very, very accurate drawings, very accurate. For us in 2021, I mean, we have so much technology now. We don't necessarily have to spend, back in like 2000, I think 2000 was the first year I ever taught Cal 1. Back in 2000, we spent like 2 weeks on curve sketching because you just couldn't go to a computer and graph something. I mean, you could get a graphing calculator and do okay, but now, I mean, Desmos, GeoGebra, there's all these graphing utilities that are free. So we are going to cut back on this a little bit. I'm not saying we're going to skip it. We're going to cut back. And then this one right here, we absolutely have to do. And that's like related rates. It's word problems. Students don't like them, but Newton's method, we can briefly do this. We don't have to do the whole thing. This is good for anyone who's a computer science major because Newton's method will show you how you can use a computer to find the solutions to an equation. And there's an algorithm that you could use. You could code it up. It's a for loop. I do it with a for loop and a do loop, and then you can actually find the solution to an equation. And that's the way computers solve equations. They don't do what we do. They do something else, and it's just an algorithm. All right. So that's what Newton's method is. So I'll show you the algorithm. We won't get into it too much more. And then we get into antiderivatives, which leads us into Cal 2. All right, so that's the plan. That's the roadmap of chapter 4. This is the last chapter of the class. And we're gonna do 4.1. So there's quite a bit here. We got about 55 minutes. Y'all ready? We're talking about maximum and minimum values of a function. So there's a lot of definitions here. Don't sit here and try and copy this all down. You have access to all this. So let's just make sure you understand visually what's going on. So we're going to first define what's called the absolute maximum and minimum values of a function. So if you're given a function, some curve f defined on some domain. So when I say defined on some domain, that means I'm giving you a graph of a function, and I could be giving it to you on an interval where it's just a picture on one little piece, or the whole, like the whole picture in both directions forever, or just on its implied domain. Here, I just want you to think about the domain can be either or. Okay, we can be talking about an interval or everything. Okay, just if we're given a function on some domain and some number c in that domain, so some number in there, we will call that f of c, okay, the value of the function at that point, the absolute maximum value of the function, if f of c is bigger than or equal to f of x for all x. All this means is that to call a point an absolute maximum, it has to be the king of the hill. It has to be higher than all the other points on the function, okay, absolute maximum. The absolute minimum is the same sort of definition, except that now it has to be smaller than all the other points in the function. So that would be the lowest point in a valley. In either case, whether or not you're looking at a maximum, absolute maximum, or an absolute minimum, in either case, those are called the global max or mins, or sometimes called the extreme values of the function. All right, so I'm going to show you this visually. All right, but we're just getting definitions out of the way. Think of absolute max, like I said, as king of the mountain, right? King of the hill. King of all hills, right? It's one thing to be the king of your hill, but to be the king of all hills means you're the absolute maximum. To be the absolute minimum means you're the lowest point in the valley out of all the valleys on the function. We'll see it in the picture here in just a moment. Now that's different than a local maximum or minimum. A local maximum or minimum is the same idea. Local max is the king of a hill. Local min is the lowest point in the valley. But you're only looking locally within that one particular hill or that one particular valley. You don't care about what's happening everywhere else. It's locally the highest and lowest points. So let's take a look at a picture. So here I have a graph of a function. It's continuous, right? By the look of it, I can draw it without picking up my pencil, okay? It is defined on a closed interval. I have two red solid dots at the end, so this is a closed interval. And I want us to look at the extreme values of the function. Okay, the extreme values. That means the highest point and the lowest point. Here they are. Those are what we call the absolute maximum and absolute minimum values of the function. You could also call those the global max or global min. Those words are interchangeable. Absolute max, absolute min, global max, global min. Now, when we talk about it, we're actually talking about the value of the function. So you would say that the global max or absolute maximum of this function is 856. You would say the global minimum of this function is negative 4,975. The x coordinate is where it happens, okay? So here, the x coordinate here is -5. So this function has a global maximum of 856. It happens when x is 2. This one has a global minimum of negative 4,975, and it happens when x is -5. That makes sense? Can y'all see visually that those are the highest and lowest points on the graph? Now let's look at locals. Those are local maximums and minimums. This point, if you look just locally, it's the lowest point on the graph. If you look at this point, it's locally the highest. If you look at this point, locally, it's the lowest, right? Just in this little neighborhood. Now, I didn't put it on here, but it's in the notes. When you talk about local stuff, okay, local, if a function is defined on a closed interval, the endpoints are always considered local maxes and mins. I didn't show that on my image. I need to fix it. So when we go back and look at this local, we're looking at locals right now. I need to include this would be something and this would be something. What do y'all think those would be? Do you think this point is a local max or min?
It's a local max.
Max, it's higher than stuff around it, isn't it?
Mhm.
So this would be a local max. And this point over here as well would be a local max because it's the highest point around it. Even though there's no stuff to the other side, right? There's nothing on this side. All these points are below it. And then over here, all these points are below it. Does this visually make sense to you? The idea of like local max min versus global max min? Yeah. All right. Here's another example. I'm going to give you a second to look at it. Let's talk local first. See if you can. Who can tell me how many local minimums we have? That's not the same graph. Oh, wait, that's the same graph. Hold on. Did it copy the note? Why did it come? That is the same exact
It is
graph.
slightly different,
Is it?
arbitrarily different.
Oh, yeah, no, it is different. Sorry, this side's higher. Okay, so for this one here, think about how many, don't answer this. How many local minimums are there? How many local maximums are there? And then what's the global max and global min, right? So try and see if you can figure that out. And then I'm going to put them up here. Let's start with the locals, right? Now I am missing, because this is on a closed interval, I am missing this and this. Those are both what? Local maxes,
X.
right? That's a local max, that's a local max. So we have a total here of 1, 2, 3 local maximums, and we have 2 local minimums. Now, what about global max and global min? Where are they? So your global maximum is actually at the endpoint, isn't it?
Yeah,
And your global min is here. That's different than the previous problem. The previous problem, the global was inside, right? But on this graph, I raised this point up further, so it took that global max over here. Are these pretty straightforward concepts?
Yeah, this isn't.
All right, this one's different. I'm putting arrows there. That implies that that graph keeps going up forever on both sides. So think about it. Think about locals first. How many local maximums do you have? How many local minimums do you have, right? And then think about global. How many local? Where's your global max? Do you have a global max? Where's your global min? Do you have a global min? All right. Locally, that's what we have. 2 local minimums, 1 local maximum. That's it, right? We don't have endpoints now, so we can't count the endpoints at all. So 2 local mins, 1 local max. Global, what do you think for global? Do we have a global minimum?
Yeah, be at -5.
-5, that's where it occurs, right? But we don't have a global maximum. There is no highest point on this graph, right? The arrows imply that it keeps going up forever. So you cannot tell me that there's some highest point on this graph. Because as soon as you try and say there is, I can always find a point higher. So this would be no global max. So you don't have to have global max or global min. It doesn't have to happen. Think about like a 3rd degree polynomial from college algebra, right? Like look at that function right there. That wouldn't have a global max or global min, right? Because it goes down forever, it goes up forever. Now it does have a local max and a local min, but it doesn't have global stuff. We good? We understand?
Wait, just a question, might be really dumb. What is it? Can't infinity be like a global maximum because it's like it's infinitely just rising up, or is that like not? It doesn't make any sense or something.
I understand what you're saying.
Yeah,
I understand what you're saying, but infinity is not a number.
yeah.
So to say that a function has a global maximum means that there's some number that is the highest point or that the graph never goes past, right? That it achieves this number. It actually reaches that number. Like when you look at this number right here, this global minimum, -4,975, we are saying that this function takes on that value, right? This function will reach -4,975. It will reach it, but it won't go any lower than that. If you try and say infinity is a global max, then you're saying it reaches infinity, but infinity is just not a number. It's an idea, it's a concept. So I understand what you're saying, but for the definition, we need it to be an actual real number.
Thank you.
No, good question. Yeah, because there's this kind of like idea, like, is infinity a number or not, right? Is it or not? When we talk about the real number system, right? When we talk about real numbers, okay, infinity is not part of the real numbers, right? Infinity is an idea. When we've been doing the limits, right, and we've been saying x goes to infinity, we are not saying literally that x becomes the number infinity. We're saying that x is growing without bound, right? That's really what this means. X is growing without bound. It just keeps growing and growing and growing and growing. So it's a concept rather than an actual physical number. All right, let's see what else we got here. Think about it. So locally, how many local maximums do we have? 3, right? There's 3 local maximums. The local maximums occur here, here, and here. Those are all local maxes, right? Now how about local minimums? How many local minimums do we have? 2. here, and here, right? Those are local min. How about global?
Can we double up on our globals?
Yes and no. It'll depend on how you say it.
Well, because
I'm
it
gonna
looks
go
like
back.
we have 2 even heights as our max.
We do have 2 even heights here, and then we also have 2 even low points, don't we? So let me go back up to the definition, because there's a subtlety here that I want to make sure you understand. When we're talking about the global or the absolute maximums, right? These all mean the same thing. Make sure you understand that. Global is the same as absolute, okay? When we're talking about the absolute max, we are talking about the function's value, not where it happens, okay? Not the number it happens, not where it takes place, but the actual value of the function is the global max and the global min. So when we look at this graph down here, and I ask you, does this function have a global maximum? You would say yes. It has one global maximum. The global maximum of this is the y coordinate of these points, 225. That's the global maximum. Now, it happens at 2 different places, but the global maximum of the function is 225. Likewise, the global minimum of this function is -64, but it happens at 2 places. All right. So we wouldn't say that you have 2 global maximums. You would say you have 1 global maximum occurring in 2 places.
It's so like a sine function would have 1 global maximum because it's going up and hitting the same y value every time.
Yeah, the sine curve, right? The sine curve on its entire domain goes up and down, right? It has a global maximum of 1. It has a global minimum of -1, right? That's what and cosine has the same thing. What would be hard to answer is figure out where all those maximums occur, right? Because your global max occurs infinitely many places, and the global minimum occurs infinitely many places as well. So, all right, we proceed. So all of this is about, what we're trying to get at is this. Now that we have an idea geometrically of what global and global max and min look like, what local maximum and minimums look like, now the question is, if I hand you a function, right? Not the picture, not the graph, but if I just hand you the function like f of x equals, and I give it to you algebraically, can you go find me those local maxes and mins and global maxes and mins without a graph? Just, can you find it just algebraically? That's the question, right? Can we do it? So it's going to require a couple of theorems to get us there, but we have theorems that'll develop this out for us. So first theorem is called the extreme value theorem. It says that if f is continuous on a closed interval, so we're only looking on a closed interval right now. So if we have a function, think about this. You have a function on a closed interval, which means when you draw it, it's got to start somewhere and it's got to stop somewhere, and you have to connect it with something that you can't pick up your pencil, right? That's what the first condition is. If you have that happening, right? Continuous function, closed interval. Then the function attains both an absolute maximum value and an absolute minimum value somewhere. Somewhere in that interval, it has to hit a highest point and it has to hit a lowest point. That's what it's saying. Does that seem reasonable to you?
Yeah, sounds right to me.
There's no way that you can, I could tell a first grader to connect 2 dots together, and not pick up their pencil. And no matter how they do it, I'm going to be able to find a highest and lowest point as long as it's a function, right? It does have to pass the vertical line test, but that seems to make, I think that seems to make sense. So I have a couple of examples here. If I draw, so I have 2 points here, these 2. If I connect those, I'm just going to pick some way to connect them. I'm guaranteed to have a global max and min. There they are. That's just an example. if I connect those two dots with some other curve, something more interesting, right? Guaranteed, gonna have an absolute max and an absolute minimum. Have to have it. Let me do another curve. Straight line. Boring, but I do have an absolute max and an absolute min, right? The two endpoints. Oh, wait a minute, hold on. Does this one have an absolute max? This one goes forever this way. I have a vertical asymptote there. This one does not have a global maximum, does it? I thought I just said that we have to. Didn't I say we had to?
This isn't continuous though.
That's right, it's not continuous. What is the first condition of this thing? It must be continuous, right? So if you're not continuous, then all bets are off. And that last example was just to try and make you, see, hey, look, if you draw me something that's not continuous, then I'm not telling you you're going to be able to find a global maximum, all right? But if you draw me something continuous, I guarantee I'll find it. Or I should say this, I guarantee it's there. Me finding it's something else, but I guarantee it's there. That's the first theorem. Now, the next theorem is called Fermat's theorem. Now, there's some of you who know about Fermat's last theorem. This is not Fermat's last theorem. This is a different theorem by Fermat. So Fermat's theorem says this. This is an interesting theorem, but it can be misused. It says if f has a local maximum or minimum at a point C, local. So if some function has a local maximum or minimum at a point C, and the derivative exists, then I promise you that the derivative is 0. Okay, let me try and see and explain what's going on here. I'm going to draw you a graph that has a local maximum. Okay, do you agree that that graph has a local maximum? Yes? The local maximum is right there, right? That's where it occurs. So the theorem says if you have a local maximum, let's not worry about minimum for right now, just this picture. If f has a local maximum, right, at some point C, and the derivative exists. So the derivative exists here. Why does, from my picture, why does the derivative exist?
Because the function is flat at that point,
Yes, but
which means
when,
the derivative
maybe I
line
should
is
ask this.
flat.
When do we have problems with derivatives existing? Where do derivatives fail to exist?
At a
On the endpoints, where it can only approach from one direction.
Okay,
or on a sharp turn.
sharp corner or a
Yeah.
cusp
Yeah.
or a jump
Mhm.
or a vertical tangent. There were three things: corner, cusp, vertical tangent, or jump or break in the graph. Anytime you have one of those three things, your derivative can't exist. All right. This theorem is saying if your function has a local max, if it does, right, and the derivative exists at that point, then it has to be the slope of the tangent line has to be 0. So let me change my color here. So the derivative here, the tangent line here, the derivative right there has to be 0. Let me show you how this can be misused. What if I give you this? Is this point a local maximum? Is that point right there a local max? Is it the highest point in that little neighborhood?
Yeah.
Yeah, it's the highest point, right? Now, does this theorem apply? Well, does this function have a local maximum right there? It does, right? It says if you have a local maximum, which we do, right? Local max at some point, and the derivative exists. Now, does the derivative exist here at this
No.
point? No, theorem's out the door. Y'all understand? If the derivative exists here, though, we can guarantee it's 0. So this theorem, it's interesting, but it actually makes things confusing for students. So we're going to just kind of gloss over that and be like, okay, it's great. I can put it here. This theorem is very important. It states that if our function has a local max or min, the derivative exists and the derivative must be equal to 0. It does not say that if the derivative is 0, that we are guaranteed to have a max or min. That's the way it's misused. Students will read this and they'll think, oh, all I have to do is look, where's my derivative 0? If my derivative is 0 somewhere, then I'm guaranteed looking at a local max or min. That's not correct. I can give you an example of a graph where the derivative is 0 and you're not looking at a local max or min. That graph right there. So if I give you this point right here, the derivative at that point is 0. Do y'all agree the slope of the tangent line through that point is 0? But that is not a local max and that is not a local min. And so this, you can't just go figure out where the derivative is 0. It doesn't work. It's not enough. You need more. So we have more theorems that are going to patch all this up for us. Before we get to the final theorem here, we have a definition. The critical numbers of a function. The critical numbers of a function. A critical number of a function is any number C in the domain of the function such that one of these two things is true. Either the derivative is 0 at that number or the derivative doesn't exist at that number. So if we have a function and we take its derivative and we look at the derivative, anywhere the derivative is 0 or anywhere the derivative doesn't exist is a critical number. But those numbers have to be in the domain of the original function in order for us to be able to say that. We call them critical numbers because they are critical in us being able to find local maximums and minimums. They're fundamental, okay? They're critical in our analysis of functions. So anywhere a function's derivative is 0, anywhere a function's derivative doesn't exist is a critical number. Now, the final theorem. If f has a local maximum and minimum, so if it does, if you have a function, okay, you got some function, if it has a local max or min, if it does, then we can guarantee this. We can guarantee this. If it has a local max or min at some point, I guarantee you then that at that number C, it's a critical point or a critical number, which means that one of two things is true. Either the derivative there is 0 or the derivative doesn't exist. One of those two things has happened. There's no way to draw a graph that has a local max or min and the derivative either not be 0 or the derivative not exist. No way to do it. So I gave you a couple examples a minute ago. That one versus that one versus that one, right? The first two have local maxes, right? Here on the first one, the derivative would be what there?
0.
0. Derivative here?
Doesn't exist.
Doesn't exist. Derivative here?
0, but it's not
0,
a max or a
but
min.
it's not a max, right? This is saying that, look, if you have a max or min, if you do, so this is not, if you do have a max or min, it's either going to be a slope of 0 there or the derivative won't exist. One of those two things. And that is enough. That's all we need because we can put that idea together to get to our final part of this section. This is the last note of the section. And it's basically how to find the absolute max and minimum values of a function on a closed interval. This is referred to as the closed interval method. This is a major note right here. This is big, all right? Because what it says is from here on out in your life, in calculus, differential equation, doesn't matter what it is. If you have a function of a single variable, so like f of x. If you have a function of a single variable and it's defined on a closed interval, then this is how to find the highest and lowest points of that graph on that interval. This is how to do it. So we do have some conditions. To find the absolute maximum minimum values of a continuous function, you have to be looking at a continuous function, all right, on a closed interval. Then the way we're going to do it is this. First thing we're going to do is we're going to find the critical numbers. That means we're going to look at the derivative, figure out where it's 0, and figure out where it doesn't exist. We'll find those critical numbers and we'll list them out, whatever they are. We'll make a list of them. And then what we do is we say, well, look, if it has a local max or min, it's got to be at one of these points. So we take those points and we evaluate the function at those critical numbers. And when we evaluate them, that means we're going to plug those numbers into the original function and we're going to get outputs, these y values. And we're going to compare them. We're going to say, oh, where's the biggest one? Where's the smallest one? And then we also have to check the endpoints, because it could be that the highest and lowest values occur at the endpoints. And we compare all of them and we just pick the biggest number out of there as our max and the smallest is our min. So those are the steps. Like anything else in math, I think it's best if we just do an example. Once you do an example, things become a little more clear, I think. You ready? All right. So let's find the absolute max and min values of f of x equals x cubed minus 4x squared plus 1 on the interval -1, 2. So I'd like to know, if you were to graph this polynomial function on the interval -1, 2, I want to know where the highest and lowest points are. I want to know where they happen. I want to know how high it goes and how low it goes. Understand? So you can use the theorem. Okay, you can use the closed interval method here. All right, so to use this, do I have a continuous function? So is f continuous on the interval -1, 2? So when you look at f, is this a continuous function?
Should be.
Why? What type of function is it?
It's just a trinomial.
It's a polynomial. All polynomial functions are continuous. Go back in your notes when we talked about continuity. All polynomial functions are continuous. All rational functions are continuous on their implied domains. All trig functions are continuous on their implied domains. So this is a polynomial. Look, it's continuous. There's no jumps, breaks, graphs. There's no corners. There's no cusps. So this is a good function, right? Yes, it is. All right. So if it's a continuous function on that interval, then we should be able to use the steps here. So the first step is I need the critical numbers. I've seen in different textbooks them call this critical numbers, and sometimes I hear it call it critical points. You might hear me say differently depending on, I mean, from problem to problem, I may switch it from numbers to points. I think this book says numbers, but other books say points. So it doesn't matter. Critical numbers, critical points. Okay, so we need to find those first. So how do we do that? There's two things we need to figure out. What's the question here? What are critical numbers? Critical numbers are places where your function's derivative is
0 or undefined.
0 or doesn't exist, right? So to find the critical numbers, what I'm going to do is this. I'm going to find the derivative. Okay, I need to find the derivative. And then I need to set it equal to 0. And I also need to find out, does it not exist anywhere, right? It's basically the idea here, to find the critical numbers. So let me start by finding the derivative. Okay, what is the derivative of this function? Well, that should be no problem for us now, right? 3x squared minus 8x, right? That's my derivative. Okay, to find the critical numbers, now what I do is I ask myself a question. First of all, when is that derivative equal to 0? That's the first thing I'm going to figure out. And then over here, I'm going to say, when does that derivative not exist? All right, and these are like two different ideas I have. So finding out where the derivative is 0 means I need to set that derivative equal to 0. And do you remember I've told you this for like since the beginning of this class? When we were doing derivatives, I said at some point you're going to have to start setting this thing equal to 0 and solving, right? Like we're here now, all right? So now the algebra is going to, you know, come into play. So how do we solve that equation? That's a pretty easy one. It's our first problem, right? So there's different ways. I can just factor an x out, right? Right? Factor an x out, set each of those factors equal to 0. You get 0. You get 8/3. I'm not going to go through that. I trust you can get that, yes? Check to make sure these answers are in your domain. Is 0 in here? Yes. Is 8/3 in there? 8/3 is not there, is it? 8/3 is not in here. Now, that doesn't mean there's anything wrong. It just means that we do not want to look at this point because it's not in that. See, we're only looking at this function on a little window, right? Within this little window, we're trying to figure out its highest and lowest points. We have just figured out that this function has tangent lines that are 0 at certain points. Those points may or may not be within the window. This one's not. Understand? Now, I need to now think about when the derivative doesn't exist. Now, this is a more of a thinking exercise. Look at the derivative, right? Here's a derivative. Is there anything that causes that derivative to go crazy? Like, is there anything I can't plug into that?
Not to my knowledge.
It's a polynomial, right? I mean, it's
Yeah,
a very
be able to
well
put
behaved
anything.
function. I can never get division by 0 on that. There's no square roots of negative numbers, right? It's not some crazy weird inverse trig function that has domain restrictions. It's a nice function, right? So there's no numbers, nothing from here, right? Nothing. Nothing from this, right? No issues. So how many critical numbers do we have?
1.
Just one. We have one critical number. The critical number we get from here is 0. That's our only critical number, which means that if there's something interesting happening at 0, right? There's something interesting. The slope of the tangent line there is 0. It could be a local max. It could be, I'm sorry, it could be the absolute max happening there. It could be the absolute minimum, or there could be other stuff happening at the endpoints that could be more important than what's happening here. So that's the first step. I need to now take that value and I need to plug it into my original function and see what I get. So when I plug 0 in here, what do I get? To the
1.
original function. Here's the function. You just get 1, right? Into the original function, you plug it in and you get 1. So right now, here's what I know. I know that the absolute maximum of this function could be 1. The absolute minimum could be 1. I don't know yet. I just know something interesting is happening there. What I need to do next is I need to compare that to what's happening at the endpoints. Okay, so let me go look at the endpoints. At the endpoints, the two endpoints of this graph are what? -1 and 2. So let me now just evaluate the original function at the endpoints. So you got to plug this into the original function. Let me just grab it here so I can go look at it. So if I plug -1 in here, I should get -1 minus 4 plus 1. I get -3. No, I get -4. And then if I plug 2 in here, I get 8 minus, I'm sorry,
Where'd the -1 come from?
I'm plugging -1 into the function. So when I
Oh, from the
cube it,
original
it
thing,
stays
right.
negative. Yeah, into the original function. Yeah, because we're trying to figure out what is the function doing here at these endpoints. I plug 2 in here, I get 8. Take away, let's see, take away 16, I think, and then add 1. So we get negative what?
Negative
Sorry?
7.
Yeah, -7. So here's the way I want you to think about this. We're in step 3 now. We're going to compare all of these. So this first thing that we got from the critical number says that when I plug 0 into the function, I get 1. What I got here says when I plug -1 in, I get -4. And this last one says when I plug in 2, I get -7. According to the theorem, our absolute maximum minimum has to be one of these, right? They have to come from this list. So what is the conclusion here? What is the absolute maximum?
1.
1, right? This right here is where we get the absolute maximum of this function is the number 1. And the absolute minimum of this function is -7. Now, on this interval, we're only talking about on this interval. We're not talking about everywhere, just within this interval.
Yeah, I'd put money on that 8/3 being the if you extend it out, actually being the the absolute minimum of the
8/3,
overall.
yeah.
Yeah, if you extend it out past that.
Yeah, let's take a look at the graph. It is x cubed minus 4x squared plus 1. Oh, yeah, okay, here it is. Let me zoom in. Now remember, we were only looking between -1 and 2, right? We're only looking there, weren't we? And so you can see here that the absolute maximum value of this function is right there. And what is the value of the function? 1, right? That's how high it got. Now it happened at 0, right? 0 is where it happened. And then the absolute minimum is this endpoint of it. Oops, I forgot to put equals here. Equals. No. So at the endpoint here, at 2, you get -7. That's the absolute minimum. Does that make sense? Now, had I opened the window up a little bit, didn't we have 8/3 was an answer? We chunked it, right? We
Yeah,
chunked that.
it was at about 2.6.
Yeah, so let me just extend this out to 3. Okay, make it 4. No, let's go 3.2.5. There we go. If I do that, if I made my window a little bit bigger, my absolute max is still 1, right? But now my absolute minimum is happening here, right here. That's my new absolute minimum. And see the 2.66 where it happens, where it comes from is that 8/3. Make sense? But see, we weren't looking there. We were restricting ourselves between there and there. Okay, kind of makes sense. And we have a long way to go with this. We have a long way to go because this is a very basic function, right? Not very complicated. But I think this is a good time to show you how we could use this to solve a problem, like a real problem. So let's say we want to do this. All right. I'm getting ahead of ourselves. In all the years I've been teaching this, I've found this to be more successful when I start to introduce the idea of optimization now as we are doing this stuff. All right. So I want you to consider this word problem. You have 200 feet of fence. And wish to build 3 identical pens as shown below. What dimensions will give you the maximum area. All right, so I'll let you jot that down. I'm gonna draw a picture. This is the way I want this built. I want 3 identical pens. So they're gonna look like this. So this is like a top view. Okay, we're looking from the top down on these pens. I'm gonna put some chickens or something in here, right? And I've got 200 feet of fence to make this enclosure out of. And I wanna do this in a way that I build these 3 identical pens with the fence, but I want the most possible area that I can get. The most area possible. Do you understand what I'm trying to do?
Yeah,
I only have 200 feet of fence and I want to use all of it. Okay, I don't want to waste any. So I want to use all the fence. I want to build this. I want to make it. All right. So yeah, you could start thinking about different ways to build it. You know, you could say, oh, I'll make this side 50 feet and this side 50 feet, right? You could do that.
make
right?
them all
And that's
perfect
one thing I could
circles.
do. What's that?
Make them all perfect circles.
Well, that's a different problem. I want them to be
That would
rectangular.
also waste a lot of fence. Having them side by side would save a lot of material.
It could be that, yeah, that would be a waste, but these, oh, by the way, I should mention, these are rectangles. These are not necessarily squares, okay? These are not necessarily squares. These can be rectangles. So, you know, you could just be like think about it. If just the non-thinking way of doing this would just be say, okay, I've got 200 feet of fence. I'll just make this 50. I'll make this 50, right? How much fence do we have left over?
100, 25, 25,
100?
25.
So we go 25 here, 25 here, 25 here, 25 here. And if we did that, what would the area of the whole thing be? Let's see, what would it be? All you'd have to do is multiply 50 times 25, right?
Yeah, 1,250 feet, square
Is
feet.
it? 1,250, right?
Yep.
So the area of this would be 1,250 square feet. Understand?
Each individual would be 416.6
Daniel,
repeating.
what's wrong, Daniel?
I'm not sure what happened.
I have 200 feet of fence, right? So I'm just like, I'm just kind of like throwing numbers out there. I'm saying, okay, one thing I could do is I could do this is 50. That would be 50. I've used 100 feet of fence, right? And then I make each of these walls 25, 25, 25. That uses the other 100. Now I've used all 200 feet of fence, yes? And then to find the total area, all I do is multiply this times this, right? Length times width, or however you want to do it. And that would give you 1,250 square feet. Yes? That's one way I could do it, right? That's one way I could do it. But I mean, there's other ways I could do it, right? I could have decided to do it this way. Why do 50? I could have done 40 here, 40 here, right? This way, which means I have how much fence? I've used 80.
120.
At 120, I can divide that up here equally as 30 here, 30 here, 30 here. Are we gonna get the same area? Is it gonna be the same area?
No, you get 1,200 instead of 1,250.
We got 1,200. It's not the same. We used the same amount of fence, but we got a different area, didn't we? We got less.
That just blew my
I
mind.
want it done in the best way possible, meaning I want the most area possible. Do y'all understand what I'm trying to do?
Yep.
I could keep messing with numbers, right? I keep messing with numbers, but the way to do it with calculus is this. I'm just going to call this side X, okay? Let's call that X. That means this side is what? X also,
Also
right?
X, yeah.
Right? And let's call this side Y, 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 Y. Those are all the same, right? Y, 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 Y. So what I need here, or what I know, is that when I take my two x's and put them together, right? This x plus this x, I add to that the four y's. I better use up all 200 feet of fence. Y'all see that? These two x's plus the four y's together needs to add up to be 200. That way I use all my fence. That I know, right? I know this. Now, what is it that I'm trying to find the most of? It says in the problem, it says, what dimensions will give you the maximum area, right? I want to know the maximum area. Maximum area. Okay, so do we know the area of this thing? What is the area of that the figure I just drew here?
X times Y.
XY, right? XY. Just take this X, multiply that times that Y. Y'all with me? Here's the cool part. Take this equation and solve it for Y. Watch. Okay, I move the 2x over. And then divide both sides by 4. So you get y equals negative 2 divided by 4 would be negative 1/2 x plus 50. Are y'all with me?
Yeah.
This is what y has to be, right? So now take that y and plug it in here, and you have a new formula for area. Your area will be x times negative 1/2 x plus 50, right? Don't worry, later on I will go through this more formally. This is just to kind of give you a glimpse into where we're headed with this. I'm going to now distribute my x through, and look what I have. Area is negative 1/2 x squared plus 50x, right? I have a formula for the area. And all it depends on is x, right? All it depends on is x. And I actually have a restriction on x too. I know that x has to be between something. Look at your picture here. What's the biggest x could possibly be?
200.
Well, x has got to be both sides together.
Oh, yeah, 100.
100, right? I could do, like, I could sit
Yeah,
there
y
and I
could
could
be
lay
equal to
out
0.
100 feet of fence, right? I could lay out 100 feet over here, then 100 feet over here, and then I'm at a fence, and I'm basically wasting my time, right? Because that would be like the extreme, like you never want to do that, but that's the biggest x would be, right? And then the smallest x would be what?
I mean, Y? Oh, the smallest X would be
Smallest
0.
x could be 0, right? If you just don't build this side of the fence or this side of the pen. So what we're doing is we're saying we look at this area function and we just look at it on the interval 0 to 100. Don't we exactly have now, like the previous problem we just did? I mean, didn't I give you just a second ago a polynomial function and on a closed interval and ask you to find its biggest and smallest values? Right? Now what we've done is we've taken a work problem about a farmer wanting to build some fences or some pens with some fence and stuff like that. And we have converted it into a polynomial restricted to a closed interval. And we can figure out when this is the biggest and smallest possible. By doing what? Taking the derivative, right? Figuring out when it's 0, figuring out when it doesn't exist, looking at the endpoints, comparing, make a list, compare them. Biggest one's your max, smallest is your min. That makes sense? I mean, just big picture. Do you understand? It's like, it's one thing to do this, right? It's another thing to apply it to a problem. Now, I only have 4 minutes. I am going to finish this, but I'm going to finish it real fast. You'll just have to go back and review the video. Just if you can't keep up with this, that's okay. Just, I'm going to use the closed interval method. So first thing I'm going to do is I'm going to find the critical numbers. Critical numbers. So I'm going to take the derivative real fast. I'm treating this like a function of x. So this is like a prime. The derivative of that would be negative x plus 50. right? Because I just bring this 2 down, becomes negative
Yeah.
x plus 50. And that's my derivative, pretty simple derivative. Now I need to figure out when is that derivative 0 and when does the derivative not exist? Well, setting it equal to 0 is actually very simple to do, right? It's a linear equation. Just solve for x, you get 50. That's one critical number. Does your derivative never exist? Is there any problems with this derivative? Do you see fractions or square roots or anything?
No, there shouldn't be
Okay,
any problems
so
with it.
No problems, no issues. All right, so we're just going to chunk this. All right, so now what we do is we take this and we plug it into the function. We plug that into, so I would like to know the area when we plug 50 in for x. So go to your area function. It was -1/2 50 squared plus 50 times 50. So all I'm doing is plugging x in here to my area. And I believe we are going to get 1250, aren't we? Someone do that. 2,500 minus 1250. Yeah, it's 1250.
Yeah,
You get 1250. Okay, now I don't know, but that could be the absolute max or it could be the absolute minimum. We don't know yet. We have to check, right? So the next thing is I want to take the 2 endpoints I had, which were 0 and 100, and plug those into the area function. So if I plug 0 in, this is the easy one. If I plug 0 in, what do I get? It's an
0.
area. Oh, so you get 0, right?
Mhm.
Kills everything off. And if you plug in 100, go ahead and do it yourself. If you plug 100 into this, you will also get 0. All right, check it for yourself. Plug in 100, do the computation, you should get 0. Which means that if I compare these, this first one said when I plug in 50, I get 1250. When I plug in 0, I get 0. And when I plug in 100, I get 0. Right? 50 got me 1250, 0 got me 0, 100 got me 0. So I'm looking for the maximum area. So this is the maximum I'm going to have. What does it take, though, to get that maximum area? What does x have to be?
50.
50. It happens when x is 50, right? If I let x be 50, then I'll get the maximum area of 1250. Which, if x is 50, can you tell me what y would have to be?
25.
You get that from here, right here, this equation. If you plug in x is 50 here, you'll get y is 25. Okay, look, we're out of time. Look, don't worry, don't stress out about that, all right? This is really about more seeing like where we're headed with this, all right? We still need to practice doing this closed interval method. There's still a lot to do. So I would say for your homework in this section, there's nothing more in terms of theory for me to give you, okay? There's nothing more. It's more just examples. So for 4.1, you can start your homework. I would say start, do the ones that are polynomials. Those are the nice ones. And things are going to get harder. Do as much as you can. And when we come back, I will revisit this. We'll do harder problems. I hope that you'll have questions about, hey, how do we do this one? This one's hard. All right. Y'all good? Any questions?
When will you be back?
If you've got anything. I'm sorry, Ethan, what?
When will you be back?
Okay, so the plan is to be back. Well, a lot of it's going to depend on how things go. So there's a chance there might be Monday, we would have to still be in Houston. So if that happens, that shouldn't impact your class because we are on Tuesday, but I will keep you all posted. The plan is to be back this weekend, but it could be that we get drawn out further. We've got to go back to Houston at some point. It's either like 8 days away or sooner. If it's soon enough, we don't want to come home just to go right back. So we might push it now. If I stay in Houston, I'm taking everything with me to be able to Zoom from there. The issue will be that I don't know how my internet's gonna be there. So that could be the kind of unknown, right?
Yeah, good old hotel Wi-Fi.
Hotel internet, you know, I don't know, might have to pay for the business class connection or something, I don't know. But right now I have no intention of changing anything for next week. All right, it's only Thursday because that Thursday is the actual day that everything's going down, so. All right,
You be safe going up to Houston.
yeah, I know, I'm about to make that drive right now.
Yeah.
Yep,
Yeah,
here
take
it's
care.
fun. I haven't been to Houston since I was like 12 years old, so I've heard it's changed quite a bit. It's a lot of traffic from what I hear, so should be fun.